Hello, everybody. This is Michio Nato from Cypress Semiconductor. Thank you for joining today's webinar on PSoC Analog Coprocessor and also for the Sensing the World Design Contest, co-sponsored by Hackster. Today we will be covering key analog features of the PSoC Analog Coprocessor device. Go over a couple example projects from the PSoC Analog Coprocessor Kit, and finish off with a Q&A session from you guys, if you guys have any questions from the presentation. And today, the presenter for this webinar is a Cypress employee. He's been with the company for about 10 years as an applications engineer, designing projects and applications using PSoC 1, PSoC 3, PSoC 4, PSoC 5, and also this new device we have, the PSoC Analog Coprocessor. His name is Kannan Sadasivam. Also, we have Hackster.io as well, who has been very helpful with getting this webinar set up. So today, we will be covering the analog side of this device. So without further ado, I would like to hand this over to Kannan, and he will start with the presentation.
Okay, guys. We had a first session where we had a brief introduction about analog coprocessor and the different kits and what kind of collateral that you're looking for understanding this device and to work with it. We also spoke about the different features inside the chip at a high level, what kind of GPIOs, memory, and all that kind of stuff. Today I'm going to go a bit deeper into the analog specific blocks in the device, specifically what kind of op-amps you have, ADC, analog, what kind of routing, references, and some special functionality if there are any. I'll also quickly go through two small example slides of how you would use those analog features and analog blocks in this device. So in this session, the initial part, about 20 minutes, I'm going to spend talking about the analog blocks, the CTB, which is a continuous time block, which is an op-amp based continuous time block, SAR ADC, the ADC block inside this device, and a programmable reference block, which gives you multiple options of references that you can use in the device in your system. Then we'll talk about a small example of an ambient light sensing application, which uses these analog blocks we have looked at in the initial part of the session. After that, I'll go into another block called the UAB, which is a universal analog block. It's a switch capacitor based block. It'll bring up the block, show you what the block looks like, what kind of programmable options you have on the block, what different implementations you can accomplish with this block. Also go through to simple component implementations that we already have in our component catalog. If time permits, we would also go in and look at inductive sensing application, which uses the UAB in a major portion of its implementation. But if we don't have the time for that, we may push that off to the next session. And after that, we would have Q&A. So I'm going to go ahead and bring up a slide that gives you a brief overview of what the analog subsystem in this device looks like. Well, it's an analog coprocessor. A major part of it is the analog subsystem. So what you have is a programmable analog block, which has a SAR ADC in it, which is 12-bit SAR ADC, goes up to 1 megasamples per second. A UAB block, which is the switch capacitor block, which is an op-amp with a bunch of switch capacitors around it, which you can configure to become a PGA or a filter or a DAC. We'd look at all those applications once we get to the UAB slide. Then you have something called a CTB, which is a continuous time based op-amp. So as opposed to the UAB, which is a switch capacitor plate-based implementation. So the CTB ends up giving you an option of using a op-amp as a naked op-amp, a buffer, or a PGA in the continuous time sense. That's what the CTB is about. Then you have the traditional capsense block, which you can use to have capacitive sensing for touch sensing and touch implementation for implementing capsense-based buttons or sliders or touchpads, etc. We also have two comparators, which are low-power comparators, which can be used to detect variation of an analog voltage against a threshold, and you can use this to use this in the deep sleep mode of the device and use it to wake up the device from deep sleep mode too. Applications like smoke detectors or something where you have analog voltage at a specific point and you set up a threshold, and when it goes above, you wake up the device, do something once in its lifetime, so you can for most of its lifetime keep it in a low power mode. And of course you have your I/O subsystem, which has all the GPIOs which connect to all the analog circuitry through an I/O matrix or an analog mux matrix, which gives you an option to connect all the 32 GPIOs that you have in the device to any of the analog blocks in the programmable analog subsystem. So that's a brief on what are the different blocks and what the analog subsystem looks like. Now going deeper into continuous time block. A continuous time block is a block with two op-amps in it. Each of the op-amp has two types of outputs, well, three types of outputs if you think about it. Two of them are analog outputs, one with a 10 milliampere output and the other one at 1 milliampere drive strength. Then you have an output which is a comparator output, which can be used to be driven into the digital side of the circuitry. This is used when you want to use the op-amp as a comparator, comparing signals. The 10x output, the 10 milliampere output of the op-amp can be used for applications like buffers, or when you want to bring the output of the op-amp to a pin, then you want a higher drive strength because you don't want to incur any case of high output impedance where the op-amp's driving some kind of a circuitry. So that's when you would use the 10x kind of output of the op-amp. And the 1x output is really provided for internal routing, where the output of the op-amp is going to, let's say, the ADC's input or one of the UAVs. So any sort of internal analog routing is when you would end up using the 1 milliampere output. In addition, you also have a resistor array in the CTB, which gives you, which along with all the programmable routing that you have inside the CTB, gives you an option to connect the resistor array in a feedback plus an input resistor arrangement, which gives you configuration of a PGA, plus the tapping on the resistor array and the configuration of the resistors can be in such a way that you can provide a gain of up to 32x on the PGA. So that's one application of the CTB, which is a non-inverting amplifier with a gain up to 32. And thinking conversely, you could also have it as an inverting amplifier of a gain of up to 31. Now, you also have an internal switch that lets you feedback the output back into the inverting input of the op-amp, which effectively makes it a follower, which is the buffer amplifier. So you can use this to buffer signals inside the device. Remember, there are two op-amps in the CTB, so now you can have these two op-amps configured in a complementary fashion, and what you end up creating is a differential input and a differential gain output. So you can generate a differential gain circuitry. And if you drive this into your ADC, which also has a differential input, you're effectively creating some kind of instrumentation amplifier for your system. And the comparator output of the op-amp can be used to make the op-amp work as a comparator. So you have an option of enabling or disabling a hysteresis on the comparator mode, which could give you a 10 millivolt hysteresis on the op-amp. You also have a deep sleep operation for this op-amp. So the PSoC Analog Coprocessor device has multiple power modes of operation. And one of the power modes is deep sleep, where you have your CPU and all your system turned down, and all the major high-frequency clocks are turned off. All that is working is some of the low-frequency clocks and memory retention. So basically, you're not working anything that are active as far as your system is concerned, and you got to wake up from sleep every once in a while or based on an event to really do something with the system. The advantage of having the CTB to work in a deep sleep mode is that the CTB can be used as a means of detecting or responding to an analog event, and thus wake up the device. Or you could also have circuitries out there that are working in deep sleep mode, meaning when you come out of deep sleep, you don't have to expend the time for the analog circuitry to catch up, or meaning for the voltages to come back into the rails that you want them to be working at. So you could already have the bias at the right point before you get out of deep sleep, because the op-amp works in the deep sleep mode. But there are limitations to the op-amp working in deep sleep mode. There are limitations on the performance, so you need to be aware of those when you're designing the circuit. The CTB, for the user, the CTB is provided as two components. One is a programmable gate amplifier. Is a component in the component catalog of PSoC Creator. So you can drag and drop this into your schematic, double-click to open the configuration. What you get is what you see on the screen. You have an option of setting up a gain, which can go from 1 to 32x, in steps of 3 dB. You can have a setting for the power, which can go from high, low, or medium, depending on what power mode you set up for the op-amp. You have different power consumptions. So depending on your power requirement for the low power requirement for the system, you can determine what kind of power setting you need. But based on the power setting you set up, the op-amp's gain bandwidth is also going to change. So that correlation or the trade-off is something you need to be aware of when you're doing your system or designing your system. The reference input to the op-amp can also be implemented as an internal reference or an external reference. When you set it up as an external reference, you get a pin where you can bring it in as a reference input. You also have an option to determine if this block needs to work in a deep sleep mode or not. This is the same mode I was talking about in the previous slide, where you have the least power consumption, and the block is still available when your device goes into a deep sleep mode. It's not put into sleep. Apart from that, you also have an option to determine if it's an internal block that this PGA is driving into, or it's an output pin. What that option does is it determines if you want to use the 10 milliampere output or the 1 milliampere output of the op-amp. Apart from the programmable gain amplifier, you also have the naked op-amp, which can be set up and connected to 3 pins: the non-inverting, the inverting, and the output pin. And you can set up your external circuitry. This is an important mode because now you have a naked op-amp which can be used as an external programmable gain amplifier, or you can set up things like transimpedance amplifiers, or even filters using this op-amp, active filters using this op-amp. Apart from the naked op-amp mode, that component also provides you an option of a follower, which when selected makes the op-amp work as a buffer, which can be used for buffering any internal signals to an external world or internal signals to internal blocks that have lower input impedance. So all these, all the other parameters in the op-amp or the flow follower component is similar to the PGA and have similar effect on the block. So that's the CTB and the different components you have for the CTB. I'm going to move on to the SAR ADC. This is one of the most important blocks in the analog coprocessor. The reason being, this is what lets you sense your circuits. This is what lets you convert what analog signals you've been processing using your analog circuits, like the op-amps or other external circuits you may be building. And this ADC is a 12-bit ADC, 1 megasamples per second maximum sample rate when you're running a single channel. As you increase the number of channels, you decrease the number of samples you get per channel, because you're going to have to distribute that sample rate. So up to 12-bit, you can also have alternate resolution of 8 or 10 bits. And that means certain channels could be smaller resolution, and all the other channels are working at a higher resolution. The inputs can come from anywhere. GPIO could be an output of a CTB block, which means it could be a buffer output, or you could set up a PGA that gains an input signal and provides it as an input to your ADC, or you could set up 2 CTBs back to back as a differential gain stage, providing a differential input into the ADC. All that connection is possible. You could also have the output of the UAB connected into the SAR ADC, which is important now that once we get into the UAB, you'll see all the different implementations that you can get to using the UAB. You could implement things like filters, which can be helpful when you're driving a signal into the SAR ADC. Now you can pre-filter the signal to reduce the amount of noise you can see in that signal before it gets into the ADC, which is probably working at a lower sample rate at that point. It could also get signal from the AMUX bus. The reason I say this is that there could be an analog signal chain that you're building using multiple op-amps and UABs and stuff, and you want to tap into a specific signal right in the middle of that signal chain, or a node in the middle of that signal chain. That can also be done using the SAR ADC. There are multiple channels you can build on the SAR ADC. Each of those channels could connect to any of these input sources. There are also multiple reference options on the SAR ADC. You could have connect to an internal bandgap-based reference. You could also connect it to an internal programmable reference block, which we'll talk about next, where you could have 4 types of references, which are derived either out of the BDDA-based reference or a bandgap-based reference. The reasons you want to have either of those is I'll explain that once we get to the actual reference block descriptions. You could also set it up to have a reference coming from an external pin. In this case, you would end up connecting an external reference chip to the SAR ADC. Typically, when you do that, you have a very high requirement of absolute accuracy to the measurements you're trying to do. So then you would set up an external reference chip, and your ADC's errors are determined by the errors of that reference chip. So hence your reference determines how much error you'll see in your measurements. You could also have a hardware control on how the ADC switches between the different channels. So you set up your channels, and you say this is the order you want to go through those channels, and then you say you start your ADC, and the ADC keeps going through sampling continuously through those channels and keeps populating multiple registers on the output, which you can read at your own leisure and get values of converted results of each of those channels. You also have to remember this device has DMA inside it, so you can use your DMA to figure out what channels are done and pick those results from the result registers and move them to your buffers or something. So you don't necessarily need to use a you need to use a CPU to switch channels or pick data out of the ADC for each of the channel measurements, or even pick data out of the result registers of the ADC and move it to a buffer. All that can be done using the ADC's hardware and a DMA combination. You also have an averaging mode in the ADC, which again is implemented in hardware, where you could set it up to have, let's say, a 256 averaging, which means it's going to take 256 samples averaged and provide you the result. Now, when you set that up to be an averaging mode, you also have to understand that you're now effectively reducing your sample rate by 256 times, because now you need to wait for 256 samples to get to the average result. Typically, you would do this for high noise kind of signals, where you average it, thus you reduce the amount of the effect of the noise in the signal. This is the ADC component. This is the ADC component. You have so there are multiple areas in this component I want to talk about. One is the timing region, where you set up your sample rate. So remember, I said it's a 1 megasamples per second ADC, but you're not stuck to using 1 megasamples per second. You could select a specific sample rate that you need, or a specific sample rate that is precise to your application. Like if you're running some kind of an audio application, you have precise requirements for your sample rate. So you can set it up based on that. And presuming you have set up your ADC for an internal clock, all the clock settings are managed by the component. So you don't have to go out and set up a clock for the ADC and make sure the clock's output matches the sample rate that you need to achieve and all that. So once you select the sample rate, the ADC automatically sets up a clock, gives you a sample rate closest to what you have provided as your expectation, and gives you an error if you do not have, if you provided a sample rate that's not going to be supported. So that's the timing part of it. There's a sampling part of the component that gives you an option to either set up the ADC to be a continuous sampling ADC, which means once you start your ADC, it's going to keep going through sampling each of the channels and keep providing the results onto the result register. You don't have any control over when to start or stop this ADC. You can't start your ADC and then stop it at a point using an API, but you don't get to stop in between channels, or you don't get to control the sampling itself, as opposed to the sample mode where you have a single sample mode, where you have to trigger each of the sampling using your SOC signal. So once you set it up for a single sample mode, either you can select to use an SOC terminal, which gives you a hardware signal, which can be driven by a GPIO or a TCPWM or some kind of a digital resource that gives you a signal that triggers the startup conversion. So now you can use that to time your sampling. Or you could also have it in a single sample mode and use your code API to start your sampling, which means you can use your user code to start your sampling. That may be important in certain cases where you don't use your ADC as often, but when you do use it, you want complete control of your sampling. Then you have selection of ranges, the input range. So the ADC's range is determined by its reference. So generally, the range of the ADC is the range of the ADC is its midpoint, which is the analog ground or the VNEG input, against plus or minus of your reference voltage. That's in a differential case, and in a single-ended case, it only goes to the one side, which is towards the plus VREF side. So you need to have a selection for your reference voltage. So you have an option to select either a system band gap, which is a 1.2 volt band gap, which is not going to change based on VDD variations. So now that's a high PSRR kind of reference. You could also use an external terminal, which means you can bring in an analog signal coming in from your analog routing. So now we can bring in an op-amp output to your to that subterminal, or a reference from the programmable reference block into this reference of the ADC. You can also have an external pin as your reference. It can connect to an external reference chip, as I mentioned earlier. You also have an option called a VREF bypass. So this is important. When you have the bypass enabled, what you do is you enable an external pin to become your reference bypass pin. What that does is gives you an option to connect a bypass capacitor to that pin. So only when you connect this capacitor to that pin can you get to the 1 megasamples per second sample rate. If you do not have a bypass capacitor, you will be restricted to 100 kilosamples per second sample rate. The reason for this is the SAR ADC is really a switched capacitor-based model of an ADC. So it's going to switch your input into a capacitor. It's going to compare that against a reference by switching the reference into another reference capacitor. So since it's a switched capacitor that is connecting to the reference, you're going to see some amount of input impedance on that reference. So if your reference is not strong enough, it's going to have the switching is going to start having an effect on the reference itself. So and the effect increases as your sampling frequencies go up. So beyond the 100 kilosamples per second, the performance of the ADC can be affected if you do not have an external bypass capacitor. The objective of the bypass capacitor is to provide you kind of like a higher drive strength to your reference, because that capacitor is going to hold enough charge or the bypass capacitor is going to be bigger than your internal switching capacitors, that it takes away the effect that the switching is going to cause to the variations in the reference. So what the reference bypass capacitor is important to have when you have higher sample rates requirements. Meaning when you're trying to run the ADC at 1 megasamples per second, you need the bypass capacitor. If you're only trying to run it at 100 kilosamples per second, you don't need that external bypass. You can also, in a single-ended mode, you can also choose what your negative input is going to be. You choose it to be your reference or an external pin. As far as data formats are concerned, you get to choose what kind of data format you need when the channel is a differential or a single-ended. You want it to be signed or unsigned. Remember, I was talking about the averaging feature. You can set up an averaging for any of the channels. Right here, you can set up how much of an averaging you want, and it can go from two samples being averaged to 256 samples being averaged. There are three modes of averaging. One is a sequential fixed, the other is a sequential sum. The difference between and another mode, which is an interlaced sampling, interlaced averaging. So the difference between the sequential and the interlaced averaging is the sequential averaging. When you go through, let's say you have 4 channels and you're averaging channel number 2 by 256 times. If you choose to have a sequential sampling, once I've sampled channel 1 and then I get to channel 2, I'm going to have to sample channel 2 256 times and get that average before I go to channel 3. That's sequential sampling. If I have an interlaced sampling, after I'm done with channel 1, I go to channel 2, sample once, and then go to channel 3 and 4, and back to channel 2, and then sample it one more time. And thus, I keep going for 256 iterations, and then get one output out of the channel 2, while I'm not affecting the actual sample rates of channel 1, 3, and 4. So those are the 2 types of sampling. the sequential and interlaced. Depending on applications, you can use either of these. Plus, you also have fixed and sum on the sequential sampling. What that means is, in a fixed averaging mode, you have a fixed 12-bit resolution for the output of the averaging, which means every time you average, you're going to shift the result back into a 12-bit mode. So what you're going to get is always a 12-bit output, as opposed to the sum averaging mode, where the output is a 16-bit output, which is presuming that once you've done your 256 sampling, you've achieved some amount of some more bits of resolution because of the nature of the averaging itself. So you get a 16-bit result. So effectively, when you're doing a 256 averaging, you can get a 16-bit result out of the ADC. Again, you can't assume that that's going to give you 16-bit of actual precision. It's dependent on the actual SNR of the system itself. It's more of the analog design of that circuit at that point. Then you have something called interrupt limits. What you can do with this is you can set up thresholds on your ADC's output to have a low threshold, a high threshold, and you can set up an interrupt on a channel to say, if I'm above a threshold, I want to generate an interrupt, or below a threshold, I want to generate an interrupt, or between two thresholds, I want to generate an interrupt, or outside two thresholds, I want to generate an interrupt. All that can be done using the interrupt limits parameter. You can set up multiple channels. The number of channels gives you an option to set up multiple channels. Each channel can be enabled at startup, or you can enable it as you go along in your code. The moment you enable it, it becomes part of your sequencing. So you need to be aware that when you enable channels you were not originally enabling, you're going to have a difference in your sample rate on the other channels, because now you just have another channel that comes in and takes up some of the bandwidth of the ADC. You can choose resolution to be a 12-bit or an alternate resolution, which you set up as an 8-bit or a 10-bit in the parameter above. You can set up your input mode to be differential or single-ended. And then there is another mode called a filter mode, which is available only for channel 0, which uses the UAV to set up a filter in its input stage. You can select averaging for any of the channels by clicking on the averaging checkbox, which selects the averaging option. Then you have something called minimum acquisition time. So what this gives you is an option to set up an acquisition time for the channel. So you're saying my channel, my channel 1 has a signal connected to it that has a higher output impedance. Because of this higher output impedance, I need more time for that channel to settle before I can actually start measuring it. So I want to give a higher acquisition time for such a channel. So in that case, I can provide the number of nanoseconds that I want to give to acquire that channel. Typically used for high output impedance channels. But you have to understand, when you give higher acquisition time, your ADC is doing nothing for that higher acquisition time. That means you're affecting sample rate by doing that. So it's a trade-off. Then you have the limit interrupt. When you enable this, it automatically enables the interrupt limits that you set up in the above region into that specific channel, and effectively generates an interrupt based on those limits. Then you have something called a saturation interrupt, which gives you an interrupt when you saturate at either the higher end, the FF side, or the 0, 0 side of the range. That's similar to your limit interrupt, only your limits are fixed at the two ends of your range. So that's your SAR ADC component. So I'm going to quickly jump into our programmable reference block. Probably running late now. So I'm going to talk about the reference block. The reference block has two major reference sources, or I would say two reference bases. And the And the two bases of references are the internal bandgap reference and the VDDA as a reference. The internal bandgap is, think about it as a fixed 1.2 volt reference that is independent of what the VDDA is. It's kind of like a Zener voltage that you have been provided, and it doesn't depend on what kind of voltage is applied to it. So this reference is important when you're trying to do some kind of an absolute measurement of some voltage out there. You can take this reference, you can divide it by using multiple resistor dividers and get up to 16 taps, which means you have up to 16 options that you can get, which is a divided version of that reference. You also have a means to gain this reference using the same resistor taps. So all this reference options are kind of encapsulated into our component, so you don't need to really worry about what tap you're using, what resistor you're setting up, and what register you need to write for setting it up. It's all part of our component, which we'll get to in the next slide. On the other side, you have the VDDA-based references. This is important when, let's say you have an external Wheatstone bridge that's being driven by a VDDA-based excitation signal. And variations in the VDDA are going to bring in an error into the actual signal that you see in the input of the ADC. There is no way to compensate this unless you actually measure the VDDA, or you use the VDDA as a reference to the ADC itself. Such a measurement scheme is called a ratiometric measurement scheme. So when you want to implement similar ratiometric type of measurement schemes, you would end up using the VDDA as a reference source to your ADC. So you also have a bunch of resistor divider taps that you can have for the VDDA. So you can have up to 16 types of divisions on the VDDA and get those out as reference lines into your analog routing. You can have up to 4 reference lines going out into the reference into the analog routing, and they could come from either a VDDA-based resistor tap or bandgap-based resistor tap. So those are the different options of programmable references that you have. Also, if you think about this, this is kind of like a VDAC for you. Each of these references options are kind of like VDACs for you. The only thing you need to understand is all of these outputs are coming out of a resistor array or a tap on a resistor, which means their outputs are not low output impedance. That means anything that consumes it need to be aware of it. If you're connecting this to a SAR ADC or an input to a SAR ADC, the SAR ADC's input impedance is going to so the input impedance is going to be in series with the output impedance, which is this resistor circuit that you have inside the reference. So you want to be aware of that, and there's going to be a drop based on what loading happens on the consumer side. So to avoid that, it is recommended that any reference voltage that goes out of here, before it gets to an actual consumer, you want to put a buffer in between, for which you can use the CTB block. This is a component, so you can choose between the bandgap-based reference or a VDDA-based reference. You have different selection options on that drop-down menu. You can select that. You can have up to 4 instances of this component in your schematic, which means you can have 4 reference analog reference options. So those are the main analog components I wanted to talk about in the initial part of this session. We haven't talked about the UAB yet, but with the components we've seen until now, I want to quickly jump into a slide where I bring up a simple application of an ambient light sensing. Ambient light sensing is using a photodiode that is reverse biased based on the amount of light that impinges on the diode. You get a reverse saturation current that you measure. The measurement of the current is what gives you the measurement of how much light is impinging on that diode. But now the amount of current or the amount of current that you get based on the number of lumens of light that you have coming on that diode is dependent also on the bias voltage that you provide to that sensor. So the bias voltage is important. So at the anode of the diode, you need to maintain a specific constant voltage to make sure that the current that you get out of this diode is something you can characterizably deduce out of and then get a number of lumens measured out of that. For this, what you use is a transimpedance amplifier. What the transimpedance amplifier does is it takes a current input, it converts it into a voltage output. Basic implementation of a transimpedance amplifier is it's got a feedback resistor that provides a negative feedback into your amplifier circuit. What that effectively does is it provides the voltage on the non-inverting input to so it maintains the non-inverting input's voltage plus the offset at the inverting input. So hence you have the bias now set up for the sensor. And the bias is in a way also set up using a programmable reference block, which sets up in this case a 1.2 volts. Remember I said that you want to be sure that you don't load your reference. So hence you use a op-amp as a buffer before it gets into the non-inverting terminal of the transimpedance amplifier. Now that sets up the bias voltage for the sensor, and the sensor now provides a current based on the amount of light that comes in, and that current cannot flow into the op-amp, so it flows through the resistor. So that drops the voltage of the resistor, hence you see a voltage on the output of the op-amp. Now the ADC gets connected to the output of the op-amp and the reference voltage that you set up. Effectively, you're measuring the current into the current multiplied by the feedback resistor that you put in. So that voltage is a representation of how much light is impinging on that ambient light sensor. So the ADC converts that voltage. You use that to determine if you want to have a specific duty cycle on your PWM, which drives an LED, which is typically the user application of using an ambient light sensing. It senses the ambient light, and then based on if there is too little of ambient light, you decrease your backlight so that you can have better contrast ratio. Or if you have too much of ambient light, you want to increase it to match your ambient light, or the other way around in certain other applications too. You also have an easy I2C block in this application just to report what number of lumens you're seeing from your ambient light sensor. So that's your ambient light sensing application. So I was checking if we have enough time to keep going through the universal analog block. So I'm going to quickly give you guys a brief on the universal analog block, and you may have like 5 or 10 minutes to do that, and then you're going to have to push out some portion of this, which is the application implementation of this, to the next session. So the universal analog block by far is one of the so as you can see in the diagram, it's quite a complex block if you think about it. But with complexity, you also get a huge amount of advantage of programmability that comes with this block. So in a simplistic sense, what this block is 2 op-amps. So there are 2 halves to a UAB. Each half has an op-amp with input side and feedback side capacitors. If you look at each half of the UAB, it has an op-amp with the capacitor in feedback and that capacitor has switches around it that makes it a switch capacitor. So there are two phases of operation. In one phase, you charge this capacitor. In the other phase, you discharge this capacitor. On the input side, you have similar capacitors, again with switches around them. In one phase, you charge these capacitors. On the other phase, you discharge these capacitors. Now, you have control over what value you want for each of these capacitors. That's one level of programmability. You also have control over what phases you want to have these capacitor switches switching it. Meaning you could have the input side capacitor, capacitor A switching in one phase while your feedback side switching in a complementary phase. What that would do is the phase 1, the capacitor A is acquiring charge. In the phase 2, it's depositing that charge onto the feedback capacitor. And in the subsequent phase 1, the feedback's gonna deposit that charge onto the output. That is, in a way, like your programmable gain amplifier or an amplifier circuit, where you're quantizing your charge going into the input capacitor, which is equivalent to an input resistance, and you're also quantizing the charge that goes through your feedback capacitor, which is like a feedback resistance. Effectively, what you've done is you've set up an amplifier circuit. So you could use these blocks to set up amplifiers. It's just one of the simplest things you can do with this. Now think of the case where instead of having your feedback capacitor to be a switching capacitor, you make it as a non-switching, a continuous time capacitor. What you effectively have done is created an integrator circuit. So the input side is switching, bringing in quantas of charges, and you're throwing that out into the feedback capacitor, which kind of acts like a filter or an integrator that keeps integrating these small error voltages that are coming in from the input capacitor. So you could build integrators using this. You could also have multiple input channels, or I would call it multiple input capacitors. And each of those capacitors could themselves be depositing charges in same phases or alternating phases. Depending on how they are phased, you're either adding or subtracting those signals themselves. So now you could be having two signals coming in into the CA and the CB capacitors who are switching in complementary phases, effectively having a difference of the two signals. If you're on the same phases, you're implementing a summer. So if you're implementing a difference and you also have an integrator kind of implementation, then what you're implementing is kind of like a delta signal modulator. It's you're taking a delta and modulating it onto the integration capacitor, which is the feedback capacitor. In nature of this whole thing, this is also a sampling circuit with the holding of that signal being your feedback capacitor. So now you've implemented a sample and hold circuit. You could also have your input being sampled, input capacitor being sampled in one phase, and switch phases based on another signal. That is also a possibility, which is called a modulation signal. So now what you've achieved is you're having a positive gain in one phase, and then the signal, the modulation signal switches, you have a negative gain for the circuit. That is equivalent to making a mixer. So there are multiple implementations for this block, and hence it's the most programmable analog block you can find in this device. We have only started scrapping the surface of what different implementations that we can have with this block, and I've listed some of them. We already have 2 specific implementations built as components in our component catalog. We are going through this list and building more and more components that use the UAV, and we're gonna keep publishing them out in future versions of the PSoC Creator that we have coming up for Analog Coprocessor. In the meantime, I would encourage you guys to go in and look at the UAB and look at some of our materials on the web, which also use some of the UAB primitives to build some crude designs. We still haven't provided them out to you guys as components because we haven't done all the testing on it yet. But you are welcome to use some of those example projects and get to have UABs in your design because this really is the most versatile component or versatile block that you can find in our analog portfolio. I did want to go through some of the other components of the UAB, but I'm going to skip that for the next session since we're, I guess, out of time. So I think it's time for questions now.
So please, if you guys have any questions from this presentation or any general questions with the PSoC Analog Coprocessor device, please ask away. For now, I will go over the chat box questions that you guys typed in. So Kannan, the first question that will be covered, are the CTB components precise enough to do an instrumentation amplifier such that it can replace an external instrumentation amplifier solution?
So I would recommend that you go look at the CTB's performance parameters in the data sheet and compare them against what solution you're trying to replace. I don't know a direct comparison against an external instrumentation amplifier chip at this point, but I would recommend you go compare those data sheets. They have all the CTB data sheet figures, so you could directly compare those against external chips.
Okay, another question. Does a real-time clock unit exist on the board, the PSoC Analog Coprocessor board?
So there's no crystal on the board, but we can implement watch crystal-based oscillator using this device, but it's not there on the board.
Are all the blocks like integrator, summer, programmable?
Yes, they are. Like I said, when it comes to implementing something like a summer, your programmability comes to the level of what kind of capacitor values you have on the UAV, or what kind of switching frequency that you need. And all of these are implemented in resistors, which are RAM-based resistors. That means you can have code that updates them dynamically too. So yes, you can program them, and you can also program them on the fly if you can figure out what those registers are.
Okay. What are the preferred packages for the PSoC Analog Coprocessor? So the preferred packages for the PSoC Analog Coprocessor, we have a 48-pin QFN, a 48-pin TQFP, a 28-pin SSOP, and a 45-ball wafer-level chip scale package. Another question, is it possible to implement a low-pass filter with each UAV block? So we can have two low-pass filters.
Yes.
And our code examples to follow to design the low-pass filter.
So you can implement a low-pass filter using the half of the UAV block. But to implement a second-order low-pass filter, you would have to end up using the entire UAV block, which is what we've done in the filter feature in the panel 0 of the ADC. So, to answer the question, do we have code examples? We don't really have specific code examples in a filter implementation, but the filter is implemented as a part of filter feature in ADC. So you can look at that as a means of implementing that filter.
Okay, next question is about pricing and pricing for 1K units. This is from Tom Moxon. So I would like to take this offline with you. So please, you could contact me or Alessandra, the host of this webinar. I can get back to you on pricing. Another question, do and where one can read the full data sheet and full program guide. So Alexi, if you visit our website, Cypress.com, you will find all the information you need on PSoC Analog Coprocessor. You will find information on the data sheet, the technical reference manual, the PSoC Analog Coprocessor Kit, where you can download the software, the IDE, the Integrated Design Environment for PSoC Analog Coprocessor, all at Cypress.com. Following question, is it possible to connect the output of the CTB block to a UAD input?
Yes, you can. In fact, that question is important because that is one of the biggest implementation requirements for the CTB, being the one block that can implement the buffer in the entire system. So the UAD being a switch capacitor-based block, you're going to have low input impedance for some of your circuits using the UAD. So you do want to have the CTB as a means of driving that input in so that you can buffer it in. So yes, you can implement the UAD, a CTB's output into a UAD.
Okay. On one of the slides you talked about enabling an interrupt on the ADC value. Is this interrupt a one-shot, or does it continuously interrupt when in that window or value?
So it is a one-shot interrupt which you have to clear. So once the interrupt is set, it's going to interrupt you, and it's not going to accept any more interrupts on that source. But once you've gone in using using your code and cleared that interrupt, you can receive more interrupts based on the source itself.
Next question, what are the top 3 reasons to pick a PSoC Analog Coprocessor device over a regular PSoC 4? So in terms of this question, PSoC 4 has both the digital and analog resources provided to you. However, for PSoC Analog Coprocessor, the Analog Coprocessor is analog feature heavy. So there are a limited number of digital functions and blocks. So you would pick a PSoC Analog Coprocessor when you will use a analog sensor. You need to read inputs from an analog sensor that require high precision and high accuracy. So there are no top 3 reasons, but the main reason is to read high precision, high accuracy analog sensor inputs accurately and process that data and send that to a host for an application that you need to use that data for. Okay, next question. So in order to avoid the impedance issue in the CTB, if the CTB is connected to UAV internally, would you suggest to make the CTB output to external I/O, so an external op-amp buffer is used to then feed the input of a UAV?
I'm not sure I entirely understand the question. Like, So the CTV is there as a buffer to the UAV. And yes, you're right that there is an impedance issue when you're using the UAV because of the switching nature. So ideally, when you're bringing in a signal from an external I/O, you need to know what is the source of that signal coming through the PI. Meaning, whoever is driving that signal in should have an output impedance that can support the input impedance of the circuit you're building using the UAV. Else, you need to have a buffer in between that can avoid the impedance issue. It can be implemented using a CTD. It can also be implemented using an external PSoC-based buffer. But you have a CTD inside the device, so you might ask what is the CTD. Now, on the other side, if you're using a UAV to drive a signal out onto an I/O, you can still have a similar issue because, again, it's a switch capacitor output that gets out. So, in that case, you need to be aware of who is your consumer of that output. And based on that, you need to either add a CTD-based buffer or an external PSoC-based buffer. Again, a CTD-based buffer is preferable because you have.
Okay, so we are running out of time, but we have one final question. The final question is, does the board have any internal memory, for instance, for image processing?
So the board has the chip and fits memory with all you get. And that is a 32K flash and 4K of RAM. I don't think it's an image processing kind of thing. So I think it's going to have to be you connecting another memory device to it.
Okay, well, we are well over time, but appreciate everybody joining the webinar today. Our next webinar is on December 7th, United States Pacific Standard Time. So if you guys are available then, please join that webinar as well. Thank you very much, Kannan. Alessandra, do you have any comments or updates from your side?
No, thanks a lot, everyone, for joining.
Okay, great. Thank you very much, everybody.
Thank you, guys.